Thank you, Andrew. It's a pleasure to be here. And from those 30 years, I'm sure I have more skeletons in my closet than Andrew does, so I'm keeping quiet. Um, yeah, there's a great buzz in the room already, and this is a fantastic initiative. Credit to Andrew and the team for doing everything that they've done so far. Andrew asked me to talk about the CDT, and I think some of the stuff that I'll bring out it has relevance to what's gone on before. And then no pressure, but she also asked for a technical example relevant to the area we're talking about. And I've just picked on one. So I think I'll probably just get on with it. But I was just reflecting as Anna was talking, and um, she gave a quote from Donella Meadows, which is really good. But I think if Donella Meadows was here today, she would say more than ecological, social, psychological, and economic. I think she would probably add technical to that list of things. And the reason for that is it's very striking that in 2020, for the first time in the globe's existence, the anthropogenic matter on the planet was greater than the living matter on the planet. So things are accelerating in an incredibly rapid way, and that's doubling every 20 years or so, probably tripling in the next 20 years. And in terms of plastics, that means that in 2020, there were twice the mass of plastics on the planet than there were living animals on the planet. So that's just a slightly broader context of what we're talking about in terms of PLFs. But anyway, I'll stop rambling and get on with it. So this is taken from the really good PLF Revolution publication from 2023 last year. When I spoke last year, I put this up as well. Because I think these pillars are really important. And this is what coming together as collaborators in the room really means. I guess I represent the knowledge base, I represent collaborations, applied and research and innovation, policy and regulation. We sort of touch on some of those things, but really what we do is at universities is we create people. And that's where the Centres for Doctoral Training come in. And I should also say that while I'm going to talk about our new Centre for Doctoral Training and the funding that we've got for it, it's not the only one in the country. So I guess, and I hesitate to list them because I'll miss one out. I guess there are probably 10 CDTs around the country that are relevant to this challenge. So everything I say will be being replicated in York, in Oxford, in Nottingham, in Liverpool. Now I'm listing them, so I'm going to miss them. Anyway, around the country. So just a little bit of where we're coming from. We started an integrated PhD in sustainable chemical technologies back in 2009, where the real focus was on integrating chemistry and chemical engineering. We were speaking slightly different languages at the time. And we had 10 cohorts of that EPSRC CDT, about 150 students. And then we stopped getting that funding, but we had cohorts within the centre that has recently become the Institute for Sustainability and Climate Change at the University of Bath, which incidentally brings together the sustainable chemical technologies, that's my expertise, together with sustainable systems and societal transformations. So it's really trying to bring together those systemic strands that we've heard about already today, and I'm sure we'll hear a little bit more about. But we have all these methods of doctoral training, and as I said, we've just inducted actually the first small but perfectly formed cohort of our new CDT in sustainable chemical technologies, and we've subtitled this a systems approach, and there's a reason for that, and I think the reason for that is that inculcating systems thinking in chemical technologists is absolutely essential for the challenges we're facing. And this particular challenge is really an archetypal challenge. There are many others around, and Annette mentioned the UN Science Policy Panel that's bubbling up in chemicals, waste and pollution. It's absolutely essential for all of the breadth of these things, but PLFs are ahead of the game, and we're delighted to be part of it. But hopefully, I think that the blueprint that's being formed here between the people in the audience and the great team running this, the blueprint can be rolled out to all sorts of other interesting areas of technological challenge that we have. So we have existing PhD students, and I don't really want to dwell on this, but they're interdisciplinary, and we'll come to that later. But I do want to say a word about the 10 cohorts that we delivered the integrated PhD in sustainable chemical technologies for, because when we'd finished those 10 cohorts, well, they finished probably 2 years ago, the last students, or 1 year ago, even the last students graduated from those 10 cohorts. We were very proud of what they'd achieved, but it's important, and this is important generally, to articulate those achievements in terms of impacts beyond what we normally think of as academic impacts. So we commissioned a report from Warwick Economics, actually, and again, this perhaps is not unique. I mean, we're proud of what we've done, but other CDTs have done similar things. We graduated 150 doctoral students. 7 out of 10 of those are working in industry. Now, that is unusual, actually, in the engineering physical sciences in the UK. That's a very high proportion. The important thing is the depth of the research that the students do is absolutely vital to their education and training, and vital to the research efforts of the universities involved. PhD students are really the engines of the research we do, particularly in the disciplines that we're talking about. So those students produced over 500 publications in that time. So that's non-negotiable. That's what they do. Having said that, they also were involved in and produced 8 spin-out companies. They did 88 internships with companies, and a reasonably conservative estimate actually generated 50 million of direct and indirect GVA to the UK economy. That's without taking account of the companies and the value they add in companies. That's the economic value they add themselves as individuals. And of course, it's an international effort as well. These are global problems. So that's part of the value of investing in doctoral training, I think. The vision for the new centre that we got is to train about 70, maybe more than that, scientists and engineers to embrace a whole systems approach in developing and implementing, importantly in implementing sustainable chemical technologies. Of course, it's no good if they stay on the bench. Our job is to generate things on the bench, but we need to make them implementable. There's a whole list of things there. Sorry, I've used the word waste, but I did at least say that we were going to valorize it. But this is all about carbon. And we've heard this. I don't need to dwell on this at all. Actually, this isn't a million miles away from the great figures that both Jen and Pete produced earlier. So 20-30% bio-based, 20-30% CO2 based, and the rest optimistically from the Nova Institute in 2020 recycling. I note that in the UK that's now been replaced with 20% of fossil resources still being used, which is sensible because that's sort of where we are. But we need carbons. I just want to say a word or two about how are we going to integrate systems thinking into our CDT training. And please don't read the whole slide. I really just want to think a little bit about how we do this and how we do it appropriately for scientists and engineers. Chemists at universities are not renowned for systems thinking. You get systems biology, you get systems engineering. Systems chemistry means something a bit odd, and I'm not quite sure what it means. But what we mean by systems thinking is having that depth of understanding of the science that you're doing, seeing the trees, if you like, but having an understanding of the forest as well. Not necessarily being an expert in material flow analysis or life cycle assessment, but being conversant in that and being able to talk to experts in it and being able to articulate those issues to a general audience. So there's all sorts of things going on here, but there's systems thinking in some of these other things as well. But formal courses in things like sustainable development, circular economy, resource efficiency, industrial ecology, which probably brings together life cycle assessment, material flow analysis, techno-economic assessment in an ecology type system. And importantly, green chemistry and process metrics, because we have to make sure that what we do, and I've got an example of this later on, what we do is appropriate to the level of development that we're at, or the point in development that we're at. These are the partners in the CDT. Many of these are in the room. These are the initial partners who helped us get the funding for the CDT. You'll see there's big companies there, small companies, many involved in this initiative. There's regional actors in there. There's international universities. There's government departments, and that's important in bringing that sort of group of people together to give the students in the Centre for Doctoral Training that really broad understanding of the societal aspects of what they're doing as well. And something I want to just say a word or two about is the integration, let's say the entrepreneurship, and I think this speaks a little bit to some numbers that Pete put up earlier. We have an innovation centre called ICAST. I've got a slide. I've probably got these slides the wrong way around. I'll tell you a little bit about ICAST later on. But our proposal for this Centre for Doctoral Training is to integrate the PhD students closely with this clean tech cluster that we have of small and innovative companies. And then you don't really need to worry about all of this stuff, but it's very important, all these additional activities that the students do. So let's tell you a little bit about ICAST for those of you who don't know it. It's a Oh gosh, sorry, the font's gone a bit funny there. That's a map for you. Let's take a step back. This is a Research England funded initiative between the universities of Bath and Oxford, and you can see this is an accident that we're doing a double act here, but we did a double act when we launched ICAST as well. Charlotte and I are the co-directors of this innovation centre. And really what the innovation centre is about, it has about 125 companies as members of the centre now. We deliver sort of agile de-risking for investment in translating research in sustainable chemical technologies from the bench through to commercialization. And we work with a number of those companies. We also work with the high value manufacturing Catapult, the CPI and NCC are vital partners. We work with Set Square, which is a university incubator working across the south of England, some fantastic people there, and with regional partners like Swindon and Wiltshire, Swindon Borough Council. And really, I think there's a number of case studies that I could articulate a bit further, a number of companies we're working with. I don't have time to do that today, really. But again, I wanted to just focus on in the nearly 3.5 years of operation of ICAST, the value that this de-risking investment in companies, and it's exactly what Pete had numbers for, which I don't have numbers for, and it was really interesting to see, was the number of very small, high-tech, highly innovative, scalable companies in the UK in this space is large. What happens is that there's a valley that was all sorts of valleys of death, but there's a valley of death somewhere where they don't get the investment. We ran an event for investors last week, and it was fantastic. They want to de-risk their investments, and they want to understand the technologies better. And that's the next sort of phase of what ICAST is doing, is really co-locating, and I mean in a virtual rather than necessarily in a physical sense, but co-locating the academic researchers with ideas, the small companies who can make commercial reality of things, and the investors who can make those small companies bigger companies. And that adds real value to what we're doing. And we have the main mechanism within ICAST is what we call joint industry projects. They're short, agile projects that are feasibility or proof of principle studies. We've done about 40 of those. I think about 29 have finished. There's 11 or so ongoing of those at the moment, and we'll deliver about 50 by the end of the project. But that's for an investment from UKRI of 0.9 million towards these projects. It was a £6 million grant, but a lot of it's for other things. The companies themselves invested 1.3 million in those, and the investment in the companies following a joint industry project and the projects that they have secured amount to about 12 or 13 million so far. And of course, that's a movable feast. That's gathering pace all the time. Some of these projects aren't even finished yet. And of course, it's also leveraged, as Andrew mentioned, first of 18 million in research grant income, which is a virtuous circle, because of course that feeds the companies and the whole ecosystem itself. And that 18 million is largely ICAS underpinning both the sustainable chemicals and materials manufacturing hub that I think Charlotte might say a word or two about later, that's just begun, and our CDT in sustainable chemical technologies. So I think it's important to articulate these benefits. I'm sorry if it's a little bit too number heavy for people. I'm just going to wrap this up by thinking about what the key features are of our PhD students. Depth of research, we said, they're definitely collaborative, interdisciplinary, and sustainability intrinsic to what we do, and that's what we know how to do and what we've been doing. In terms of enhancing and supporting entrepreneurship in our students, having them closely involved with that cluster of 125 companies, plus the partners of the CDT, plus the experience of Set Squared and the high value manufacturing catapults as well. We hope will enhance the level of spin outs and startups coming from those students, although it's already quite good. And then I think the systems thinking side of it is really where we can add value to, I'm talking to the industrial people in the room here, your employees of tomorrow, which you can articulate in a different way as better understanding the threats that we have, but then also developing the science and innovation that is deployable to those to give sustainable solutions. And we've already heard that this is a complex problem with many things playing against each other, whether it's regulation, whether it's policy, whether it's economics, whether it's behavior, in fact. So I think this has all been said for me. Again, I showed this slide earlier, and this is for packaging last year. This is for packaging materials. I don't really want to say much about this, except for PLS, of course, the leakage is going to be far higher. So you can argue about these things, but what I want to talk about, and that seems to be a common theme today, is talking about renewable and sustainable feedstocks. Of course, we mustn't forget the end of life and the better material properties as we're going through life, as we're going through as well. These are all important things. But I'm going to say a little bit about new feedstocks. And I thought a little bit about the technical example to just give you a flavour of that Andrew wanted. And I thought it would be good to just present a very specific case of something that we've been developing over the last 2 or 3 years that we've recently published, and I think it's a really potentially a really interesting platform for renewable materials. Of course, everybody knows that HMF derived from sugars and cellulose is a platform chemical, and everybody knows that FDCA, the diacid of that, is used to make polyesters. And it's a really interesting platform chemical in itself. We've been doing work on polyamides, on semi-aromatic polyamides, and I'm not going to talk about that. What I am going to talk about is utilizing diformylfuran, DFF in this case, summarized on this slide, but I'll go into a little bit more detail. And this is a project that came about from a collaboration actually within the UK Catalysis Hub, which is another really interesting part of this whole ecosystem and equation, where we, and again, you can go from HMF to FDCA chemically, high temperature, high pressure. But Nick Turner in Manchester was just showing me that he developed a route, and it's published down here, a biotech route to selective oxidation of HMF to DFF, and DFF is an interesting molecule, but it's been used far less to make polymers. So there's this route available that's scalable, and the question really was, what could we do that's interesting with this to make polymers? So these are molecules with established credentials as sustainable. I'm not saying that they're ultimately the ones we will use. but there's a lot of evidence that these are sustainable bio-based platform molecules of the future. So we started a project on this, and Mohammed Cameron, a brilliant student of mine, came up with this cross-aldol reaction. And again, I haven't really got much time to dwell on this, but if we take the DFF and we take this aldehyde, which is of course derived from castor oil, so it's 100% bio-based, and again, that's an established bio-based platform. So these aren't exotic molecules at this stage. We can make these alpha omega dienes by a cross-aldol reaction at multi-gram scale in good yield. And if you look at this molecule, there's all sorts of interesting things we could do with it, and I'm sure you can come up with other interesting things. It's a highly functional monomer for polymerizations, and you can make your own polymers out of it. You can do what you want with it. And at this point, I think it's worth stressing that what we're doing here is we're looking at the green chemistry metrics of this process at the moment, because it's at that appropriate scale that we do that. We don't want to do a full life cycle assessment on this. It would bog us down, and it wouldn't be accurate anyway, and it wouldn't compete with things that are working. But what we want to know is whether this molecule is, in principle, has the fundamentals to be a sustainable platform and a building block. People have made related monomers before, and we took some very simple metrics here: atom economy, atom efficiency, simple E factors, reaction mass efficiency, and ours sort of wins on all counts. So that's almost a back of the envelope calculation that tells us, in combination with the fact that we know there's supply chains for these sorts of materials, and potentially high volume supply chains, we know that this is feasible to take further forward. Again, just a couple of minutes on this. We did ADMET polymerization on these and got some reasonable molecular weights on these sorts of things. They have low glass transition temperatures, as you might imagine. They're pretty stable polymers. The degradation temperatures are high. We can coat paper with them, and they're pretty hydrophobic, again, which is what you might expect from these things. And also we can modify the polymers post polymerization. We can make alcohols out of them. We can do reductive amination and make amines out of them. And you can see, and I won't show you all the data, but you can see the infrared tells you that the right things are going on. The physical and mechanical properties of the polymers do as well. And then, of course, there's many other things that we can do with any of these polymers once we've got them, both at the monomer stage or post polymerization. So that's a very early stage example, I think, of a platform that we'd really like to take further forward. And to take it further forward, we need applications. So we need collaborations with industry partners to do so. And in summary, I just wanted to put this slide up again, because I think it's really important, and it does summarize exactly the pillars that we should be leaning against to make this thing happen. And it's great to see all these people in the room, and I think I'll finish there. Thank you.
Thank you very much, Mohammed. I have one question, but I'm actually down to ask you a question. Maybe I'll ask that. I might be lower than this, but there's anybody else that wants a question? I'm trying to see if Lily has a question, and I can ask a question. Ah, great. I can ask you a question. Excellent. Matthew, thank you very much for a great talk, really. I mean, there is this thing going on in industry about, formulation that you can just have a new material that can just be automatically dropped in. But I, as a formulator, know that that's very difficult. It's all those colloidal interactions that happen, and it really calls out for the formulators here to think about these novel approaches. So could you just sort of tell us whether we use the same polymer architecture, drop in, draw, and take out, or is there scope for new sort of polymer architectures that would have this end of life embedded in it?
So yeah, I think that's a really interesting general question. Is where do we go? Do we stick with the architectures we got, or do we start to develop new things like the very early stage thing that I showed there? my view of that is that we have to do both, and that's the answer to many of these questions for sustainability. Is I think our job as a community is to again, I think Anna said something about the sort of temporal aspects of the complex problem. We need to do things now, but we also need to have a war chest for 10 years time, 20 years time, 30 years time. So we need options. I think we would fossilize, if it's not a horrible word to use, if we didn't continually be developing these options and new things, as well as just moderating the formulations we've got. I mean, I hear from formulators that quite often formulations are so complex, everybody's forgotten why a particular thing was in there, but nobody dare change it in case it does something awful. So, I mean, if in the formulation, if you can use new materials in a formulation and get the same effects, then presumably there are significant advantages in changing the materials to new platforms. And it might be something simple like, you know, the aromatic ring from a furan rather than that from an arine. But it might be more complex and these sorts of things and many others. This is, of course, isn't unique. Many other platforms offer almost too many variations, and the space that we're searching for effects is I think what you hinted at earlier on is very broad. But again, there's ways of addressing that in the future.
Thank you very much, Matt. I just want to make a plug actually. You said thanks.